electric field intensity. Electric field intensity at a point on the equatorial line of an electric dipole. Electric field intensity at a point on the equatorial line of an electric dipole. In the diagram, we consider two equal and opposite point charges placed at a certain distance. So this is a negative point charge, minus q be the negative point charge which is placed at the point A, and another equal and opposite charge, that is plus q charge, is placed at the point B. Both the charges are point charges. Two equal and opposite point charges, that means minus q and plus q charge, are placed at the 2 points A and B at a distance 12. A and B at a distance 12, and we consider a point C which is at equal distance from the two point charges minus q and plus q. C is the point which is at the same distance from the 2 points A and B. At the point C, unit positive charge, that means plus 1 charge is placed here. We can draw equatorial line, that means we can draw a straight line from the point C which is perpendicular to the axis AB of the dipole, and here Cn is the equatorial line which is perpendicular at the midpoint N of the dipole AB. Cn is the perpendicular to the axis AB of the dipole. Length of the dipole is 12. Unit positive charge, that means plus 1 charge at the point C, experiences an electrostatic force that is E1 due to plus q charge of the dipole. So E1 is the electric field intensity at the point C due to plus q charge of the dipole AB. This field intensity E1 acts along CK. That means this electric field intensity E1 acts from the point C away with respect to the plus q point charge of the dipole. Similarly, field intensity at C due to minus q charge will be acting along AB, and this field intensity, that means field intensity at the point C due to minus q point charge of the dipole, acts along CM. That means E2 is the electric field intensity at the point C due to minus q point charge at the point A of the dipole AB. We have two field intensities, E1 and E2 are the two field intensities at the point C due to plus q charge and minus q charge. Resultant field intensity of E1 and E2 is EEQ. EEQ is the resultant field intensity which acts along CX. Towards left. We can draw a rectangle or parallelogram, and the diagonal CX is the electric field intensity, resultant field intensity EEQ of the two field intensities E1 and E2. In the diagram, E1 equal E2, and we can prove that E1 will be equal to E2. To find the electric field intensity, at the point C, on the equatorial line, Cn, that is a straight line Cn perpendicular to the axial line or perpendicular to the axis AB of the dipole at the midpoint or at the center N of the two charges. That is a perpendicular a perpendicular CN, a perpendicular CN a perpendicular CN to the axial line AB and passes through the center N of the electric dipole, passes through the center under bracket capital N of the electric dipole AB, A unit positive charge that is plus one charge is placed at the point C. To find the electric field intensity at the point C on the equatorial line, a unit positive charge that is plus one charge is placed at the point C. The electric field intensity at the point C, due to plus q point charge of the dipole AB, that is the electrostatic force of repulsion experienced by the unit positive charge experienced by plus one charge at the point C due to plus q point charge of the dipole AB at the point B, bracket closed, is given by E1 equal 1 by 4 pi epsilon 0 Q divided by BC whole square. E1 acts along CK which is parallel to BC. Since BC equal root over Cn square plus NB square equal root over R square plus L square equal 1 by 4 pi epsilon 0 divided by root over R square plus L square whole square. Therefore, E1 equal 1 by 4 pi epsilon 0 Q divided by R square plus L square. E1 equal 1 by 4 pi epsilon 0 Q divided by R square plus L square. This is the electric field intensity at the point C on the equatorial line due to plus q point charge of the dipole, where 12 is the length of the dipole. 12 is the length of the electric dipole AB and R is the distance of the point C. R is the distance of the point C on the equatorial line from the midpoint N of the dipole AB, from the center N of the axial line AB of the electric dipole. R is the distance of the point C from the center N of the axial line AB of the dipole. Now E1 is the electric field intensity at the point C which acts along CK from the point C away with respect to plus q charge of the dipole AB. E1 is the electric field intensity which acts along CK away with respect to the plus q charge of the dipole AB. This field intensity, that means E1, acts from the point C, comma, away with respect to plus q charge of the dipole AB, away with respect to plus q point charge of the dipole AB, plus q point charge of the dipole AB, and at an angle theta, we can denote the direction angle at an angle theta with the axial line with a straight line Cx which is parallel to the axial line AB, or also we can say that this field intensity E1 acts from the point C, and we can denote the angle theta in the diagram. Angle CBN is theta. Similarly, angle KCX is also theta. That means E1 acts at an angle theta with the direction Cx or with the axial line AB of the dipole. Axial line AB of the dipole. Similarly, the electric field intensity at the point C due to minus q point charge of the dipole AB, that is electrostatic force of attraction experienced by plus 1 charge at the point C due to minus q point charge of the dipole, is given by E2 equal 1 by 4 pi epsilon 0 q divided by Ca whole square. Here we did not use the sign of the charge because sign of the charge is not used in the expression of electric field intensity or force, where Ca equal root over r square plus L square, and r is the distance of the point C. R is the distance of the point C from the midpoint in of the dipole AB, and E2 acts along Ca. That's why charge Q should be divided by Ca whole square, not AC square. Field intensity E2 acts from the point C towards minus q charge, and r is the distance of the point C from the midpoint in of the dipole AB, equal 1 by 4 pi epsilon 0 q divided by root over r square plus L square whole square. Therefore, E2 equal 1 by 4 pi epsilon 0 q divided by r square plus L square. E2 equal 1 by 4 pi epsilon 0. Therefore, E2 equal 1 by 4 pi epsilon 0 q divided by r square plus L square. And this field intensity acts from the point C towards minus q point charge of the dipole AB, towards the minus q point charge of the dipole AB. Therefore, the resultant electric field intensity of E1 and E2 is given by E equal root over E1 square plus E2 square plus 2 E1 E2 cos 2 theta, where angle subtended by the straight line CB with the axis is theta. Similarly, E1 acts at an angle theta with Cx, and E2 acts at an angle theta with the direction Cx. That's why angle between E1 and E2 is 2 theta, equal root over 2 E1 square plus 2 E1 square cos 2 theta, since E2 equal E1. Two field intensities E2 and E1 are equal. Root over 2 E1 square is taken common under bracket cos 1 plus cos 2 theta, root over 2 E1 square dot 2 cos square theta, root over 4 E1 square cos square theta. Therefore, EEQ, this resultant field intensity should be EEQ equal 2 E1 cos theta. 2 E1 cos theta. Putting the expression of E1 and cos theta, we get 2 1 by 4 pi epsilon 0 q divided by r square plus L square. In place of cos theta, we can write an divided by Ca. Theta is the angle subtended by the straight line Ca with the axis AB. Similarly, theta is the angle subtended by the straight line CB with the AB. In place of cos theta, we can write L divided by root over L square plus L square, where cos theta is equal the base an divided by hypotenuse AC equal L divided by root over r square plus L square. Here the hypotenuse CB is equal to root over r square plus L square, where r is the distance of the point C from N and L is the distance of the plus q charge from the midpoint N. Therefore, EEQ equal 1 by 4 pi epsilon 0 q dot 2L divided by r square plus L square, bracket closed, to the power whole to the power 3 by 2. In place of q dot 2L, we can write P. Therefore, EEQ equal 1 by 4 pi epsilon 0 P divided by R square plus L square whole to the power 3 by 2. EEQ equal 1 by 4 pi epsilon 0 P divided by R square plus L square whole to the power 3 by 2, where P equal Q dot 12. P small p equal Q dot 12, where which is the electric dipole moment of the dipole AB. P equal Q dot 12, which is the electric dipole moment of the dipole AB. Therefore, if we draw the diagram again, so this is the electric dipole consisting of two equal and opposite charges. Dipole moment vector P acts from minus Q to plus Q charge. We can draw equatorial line. We can draw the equatorial line Cn. Unit positive charge plus 1 charge is placed at the point C. This unit positive charge, that means plus 1 charge, experiences an electrostatic force EEQ. So EEQ is the field intensity at the point C on the equatorial line. 12 is the length of the dipole. Field intensity EEQ acts along Cx in the opposite direction of dipole moment vector P. Dipole moment vector P. It acts in a direction Cx. In a direction Cx opposite to the direction of dipole moment vector P, which acts from minus Q to plus Q charge. Therefore, vector EEQ equal EEQ minus P cap, where P cap is the dipole moment unit vector or unit dipole moment vector, equal 1 by 4 pi epsilon 0 P divided by R square plus L square whole to the power 3 by 2 under bracket minus P cap. Therefore, vector EEQ equal minus 1 by 4 pi epsilon 0 vector P divided by R square plus L square, vector P divided by R square plus L square whole to the power 3 by 2. This is the vector expression of field intensity at a point on equatorial line of a dipole in vector form. Negative sign indicates that this field intensity vector EEQ, in the diagram, the field intensity vector EEQ acts along Cx from the point C to X towards left, and dipole moment vector P acts from minus Q to plus Q charge of the dipole. Vector P means dipole moment acts from A to B, that means along the axial line AB. Dipole moment vector P acts along in this direction from minus Q to plus Q charge. Vector P acts from minus Q to plus Q charge towards the right, but field intensity vector EEQ acts towards left. So vector P, dipole moment vector P is the dipole moment vector of the dipole AB, which is the product of charge and distance vector. Dipole moment vector which acts along AB, that is acts from minus Q point charge to plus Q point charge of the electric dipole AB. This is the electric field intensity vector at a point on the equatorial line. Vector EEQ acts towards left in the opposite direction of dipole moment vector P. So this is vector EEQ equal electric field intensity vector. Electric field intensity vector at the point C on the equatorial line, Cn, at the point C on the equatorial line Cn, at the point C on the equatorial line Cn, which acts along Cx, that means which acts along the straight line Cx in a direction opposite to the direction of dipole moment vector, which acts in a direction that is along Cx, which acts in a direction that is along Cx, opposite to the direction of dipole moment vector vector p opposite to the direction of dipole moment vector under bracket vector p, dipole moment vector under bracket vector p. Additional information again, if the electric dipole AB is short, that is 12 much less than R. If the dipole AB is very short, in that case 12 will be much less than R. Here 12 is much less than R. R is the distance of the point C from the axial line AB, and 12 is the length of the dipole. Therefore, EEQS, that is the field intensity, will be 1 by 4 pi epsilon 0 P divided by R square plus L square whole to the power 3 by 2 equal 1 by 4 pi epsilon 0 Q dot 12 divided by R square plus L square whole to the power 3 by 2, 1 by 4 pi epsilon 0. Now, if neglecting L with respect to R, as 12 is much less than R, that is assuming L as 0 with respect to R, neglecting L with respect to R as 12 much less than R, that is assuming L as 0 with respect to R, then L plus R will be approximately equal to R, and R minus L will be equal to R, and R dot L, that is very important, R dot L will be equal to R dot L. That will not be equal to 0, because if we neglect L with respect to R, in that case we have to assume L as 0 whenever L is added with R or subtracted from R, provided 12 much less than R. 1 by 4 pi epsilon Q dot 12 divided by R square plus 0 whole to the power 3 by 2, 1 by 4 pi epsilon 0 P by R cube. Therefore, EEQS equal 1 by 4 pi epsilon 0 P by R cube. EEQS is a field intensity, electric field intensity at the point C, at a point on the equatorial line, of a short electric dipole. Field intensity at a point on the equatorial line of the short electric dipole. We can draw the diagram again. This is a short electric dipole consisting of minus q plus q charge. Vector P is the electric dipole moment vector. We can draw, this is what equatorial line, and this distance small r is much greater than the length of the dipole 12. R is the distance of the point C from the axial line of the dipole. Plus 1 charge is placed at the point C, and along Cx, plus 1 charge experiences an electrostatic force vector EEQS. Vector EEQX acts along Cx, that means towards left, and the distance r is much greater than 12 for a short dipole. 12 is the length of the dipole or distance between minus q and plus q charge. Vector 12 is the distance of plus q charge from minus q charge. In this case, vector EEQX is equal 1 by 4 pi epsilon 0 PR cube minus P cap, where P cap is the unit dipole moment vector. Here we can consider a vector having magnitude 1, and P cap is parallel to vector P, means unit dipole moment vector is parallel to dipole moment vector, and here vector EEQS equal minus 1 by 4 pi epsilon 0 vector P by R cube. This is the electric field intensity vector, which acts in a direction, that means along Cx, in a direction Cx opposite to the direction of dipole moment vector P, dipole moment vector P. Additional information, that is field intensity is directly proportional to 1 by r cube due to a short dipole. That means field intensity, again field intensity is proportional to 1 by r square due to a point charge. Due to a short dipole, field intensity is inversely proportional to cube of distance, and due to a point charge, E proportional 1 by r square. Here we know that due to short dipole, E eqs equal 1 by 4 pi epsilon 0 p by r cube. That's why E proportional to 1 by r cube, and and also due to a point charge, field intensity has the expression E equal 1 by 4 pi epsilon 0 q by r square. That's why E proportional 1 by r square due to a point charge.